I'll begin this afternoon session with a brief introduction. Welcome to the Canadian Institute of Forestry's National Electronic Lecture Program. My name is Sharon Young, and I will be hosting today's session. Today is Tuesday, March 18th, 2025, and this is the seventh session in the lecture series entitled Advances in Operational Forestry, Tree Planting, and Carbon Mitigation Research. This series is a collaborative effort coordinated between the Canadian Forest Service and the Canadian Council of Forest Ministers. The CIF-IFC is very pleased to collaborate and host these webinars. For today's session, we are pleased to have Ronnie Drever, who will give an exciting presentation titled Restoring Forest Cover at Diverse Sites Across Canada Can Balance Synergies and Trade-offs. To kick things off, Ronnie works as a senior conservation scientist for Nature United, the Canadian affiliate on the Nature Conservancy. He provides science leadership and capacity to develop collaborative research with a variety of partners, all in the service of decision and policy relevant information for implementation of natural climate solutions and wildlife conservation. In 2021, he led the publication of Canada's first comprehensive assessment of nature-based climate mitigation. He holds a Ph.D. in biological sciences from University of Quebec in Montreal and a master's in resource and environmental management from Simon Fraser University. With that, I will now pass it over to Ronnie.
Thanks very much, Sharon. It's my pleasure to be here with you, and thank you, Connie, for joining this webinar and here to about this forest restoration study we published at the beginning of this year. So this work included a couple of co-authors from the Natural Resources Canada, and Katie Fisher, Werner Kurtz, and Zach Zhu. So which may be of interest to this audience. And really what we tried to do with this research is to provide decision-relevant information to support Canada's globally important commitment to tree planting. This commitment aims to tackle climate change and reverse biodiversity decline. And we think it can be an example for other large-scale tree planting efforts around the world. The key message I'd like to deliver to you today is that there is lots of area in Canada where we could restore forests. We find in the paper that there's about 19.1 million hectares where restoration could be deployed, which is quite a large area. It's about twice the size of Lake Superior. And actually, and considerably more than is what is needed to meet Canada's commitments to 2 billion trees. We also find that in the paper that realizing the multiple goals that people have for forest restoration requires capitalizing on some of the synergies and addressing some of the trade-offs that are inherent in these types of decisions of where to allocate tree planting effort. And these trade-offs and synergies are best addressed using a portfolio approach that is essentially targets different objectives in different areas, and then cumulatively, we think that can provide the most or the best outcomes for all the things that people desire from new trees. So I'll just jump right in. This crowd probably doesn't need to learn too much more about the 2 billion trees effort, but it was really the basis for this research. As Sharon mentioned, my team at Nature United, we're really focused on applied research and policy relevant research. So when Canada in 2021 made this commitment to tree planting and forest restoration, we recognized that there was essentially an issue with this ambitious program, which this program aims to essentially in collaboration with Indigenous communities, landowners, municipalities, etc. It wants to essentially help achieve Canada's emissions reduction goals, create habitat for species at risk, and improve human well-being. But because the program is voluntary, which is appropriate, meaning that when a program like this is voluntary, it kind of bakes in the consent that's needed from land managers and land stewards for restoration. But it does mean that there was no systematic analysis of where these practices should best take place. And so that's the goal that's the information gap that this research tried to fill. And to do that, we brought together a diverse team of researchers from academia, NGOs, and from government. We came up with the research I'll be presenting on shortly. I will say that this work had 2 billion trees in mind, but irrespective of this policy commitment and that program, that federal program, I think this research has currency beyond those commitments. The need for forestation is not going away, irrespective of what happens in terms of federal funding. And this research has value in that respect. Okay. So the first thing that we did is to try to characterize what we call the area of opportunity for forest restoration. So in other words, if you were going to restore forests in Canada, where would you do it? And as I mentioned a minute ago, that we found 19.1 million hectares are possible for forest restoration in Canada. And this is forest cover restoration, i.e. so bringing back forests where they used to be, but are not there now, which is kind of a categorical difference from forest restoration that aims to build back forest function in places where forests already exist. So just bear that in mind as you think about what we mean by forest restoration in this context. So in essence, we started off, where are forests in Canada naturally occurring? And that was sort of our play space. And then we started essentially a series of subtractions from that area. We took out really any places that are present providing high quality agricultural land. We took out places, for instance, that are in the agricultural land reserve in BC. We took out places that are wetlands and cities and another sort of land cover that's inappropriate for forest restoration. And really what we came up with is a map that tries to, that focuses on low quality agricultural land, particularly in the southern boreal forest, as you see here. It also identifies the areas that currently map as shrublands or grasslands that are burned areas that haven't naturally restocked to trees yet. And it also identifies large areas in southern Ontario and Quebec and in the agricultural lands of the maritime provinces of Eastern Canada where we could bring back forests. And then so with that area of opportunity, we then stock that 19.1 million hectares with variables or I would say traits that respond to the types of things that people care about when they think about forest restoration. Growth rates seems like a pretty obvious one, and that's or above ground carbon accumulation. So we relied on a novel model that it was a global set that we brought it down to, we downscaled it to Canada. And then so for each of these pixels in our area of opportunity, we assigned it a per hectare per year growth rate of above ground carbon accumulation. Then we looked at, spent a lot of time trying to understand the costs associated with forest restoration, the idea being that ideally we want to target areas where the costs are low. And so this economic analysis considered implementation costs that were a function of the types of trees that we bring back to these proposed sites, as well as the slope on that site. And this is sort of broad categories of tree types. So there's like conifer, mixed or deciduous trees. And so typically, in northern areas, we think about bringing back conifers, southern areas, mixed trees, mixed composition of trees. And in places like southern Ontario and Quebec, bringing back deciduous trees. And then we tried to get a sense of the foregone opportunity costs of bringing back land to forests. And so this was estimated by the market value of agricultural lands and farm buildings and to provide us a relative estimate of foregone opportunity costs. So in this case, we used agricultural value, land value, as an estimate of foregone opportunity costs. And so as you're thinking about these numbers, I think the estimates are sort of most valuable when we think of it in a relative way, rather than thinking these are the costs in this site in an absolute term. What we're really trying to do is, what is this pixel cheaper, relatively speaking, or more expensive than the other? So then that allows us to essentially prioritize sites in our area of opportunity based on economic costs. Then we looked at biodiversity values, and there's so many ways you could try to do this, but we tried two. And I think that basically because the data are there, and there was nice recent studies to provide the information. We first looked at species at risk. So each pixel in our area of opportunity was assigned a richness score based on the overlap of different ranges of species at risk. So lots of species at risk overlapping, a high score, and vice versa. And then we looked at ecological connectivity. And so in this case, we relied on a recent Canadian effort to map ecological connectivity in Canada by Pither et al. In 2023. And so this model of ecological connectivity envisions a mobile mammal like a fox or something like that, moving across the landscape in areas that have lots of resistance to movement, i.e. other cliffs, highways, large lakes, that kind of thing, get a low score, and places where movement is less constrained get a high score. And so that's the map you see here on the right. And then we tried to incorporate aspects of people values. And so these people benefits were essentially quantified in two different ways. And they relied on a study by Matt Mitchell from UBC from 2021 that allowed us to assign to each of our pixels in an area of opportunity a score based on its capacity for nature-based recreation. So in other words, we gave each pixel a value for nature-based recreation that considers aspects like proximity to large water bodies, mountain views, and distance from high road density areas. The second attribute for people that we considered was freshwater provision. So for each of the pixels in our area of opportunity, we assigned a score based on an analysis that considers the interplay with the annual precipitation every year, as well as, and then compares that to the downstream water demand for that precipitation. So the areas that have high runoff and high downstream demand get a high value in this schema. In both these cases, the assumption implicitly was that basically site-specific prescriptions at each of the pixels would allow enhancement of these two values. And then so now I sort of describe the kind of conceptual schema of how we got to our kind of informational base. And then we ran a series of prioritization scenarios. And these scenarios essentially optimize different combinations of our input values. The first three scenarios focus on maximizing the mitigation potential, i.e. the above ground carbon accumulation, i.e. growth rates of trees, and doing so at the lowest cost. And so you'll see in the top row of the table you see on the right of the slide, the icons that depict that. So we wanted to find out where's the highest growth at the lowest cost. And then kind of the scenarios get a little more complicated as you go down the table. So in the second scenario, accessible mitigation, there we tried to characterize the highest growth that was the closest to roads. And in all these analyses, I should mention that we used an area constraint. So 2 billion trees at normal stocking densities of tree planting projects corresponds to about 1.2 million hectares. So in all these cases, we said, model, find us the areas that have the highest growth at the lowest cost, that together comprise 1.2 million hectares in that subset of the 19.1 million hectares I mentioned. That is our area of opportunity. I hope that's clear. And so as we go down the list of different scenarios, we tried to, for several of these scenarios, tried to maximize co-benefits while optimizing the amount of low-cost mitigation. And then there's a final one where essentially it was the all-value scenario where we asked the model to find the 1.2 million hectares that provide maximum amounts of all the co-benefits that we considered, and optimizing the amount of low-cost mitigation potential available in the 1.2 million hectares. Now I'll talk a little bit about some of the results. The first thing to consider is this selection frequency map that you see here. And I'll just point out that the data here are not to scale. We sort of drew them this way to essentially call out the spatial pattern that you should be able to recognize. But in general, so what this map shows is the number of times that any given pixel in our area of opportunity was chosen in one or more of the scenarios. So the blue colors, the dark blue colors, indicate areas that were chosen in at least 4 of the 8 scenarios. And then the light blue indicates areas that were chosen in 1 to 3 scenarios, and the gray colors denote areas that weren't chosen at all in any of the scenarios. And so you'll observe in this map the general pattern that the solutions in general tend to focus on areas in coastal British Columbia, the east side of the Rocky Mountains, southern Ontario and Quebec, and the maritime provinces of eastern Canada. You also notice that much of northern Canada wasn't chosen in any of the scenarios. And on this particular point, I'll say that this doesn't mean that we shouldn't think of northern Canada as a place to do forest restoration, but rather that the mitigation of climate change through tree planting should not be the primary reason we do that in these areas. For instance, we could think of forest restoration in the context of restoring habitat for woodland caribou, which is an emblematic species in our northern forests that's at risk of local extirpation. And that's a fantastic reason to do forest restoration, but it's not a good place to do it in the context of climate change mitigation. So in terms of I'll just talk about 2 of the principal scenarios that people seem to be most interested in. This one you see here now is the map of the low-cost accessible mitigation. So this was a scenario in which we asked the model to find the 1.2 million hectares that provided the highest amount of low-cost mitigation potential that's close to roads. And you'll see in this map a similar pattern that you saw in the selection frequency map, in that it identified areas in southern Canada, specifically in the temperate forest areas of southern Canada. So in the temperate forest of Ontario and Quebec, and the maritime provinces in the maritime provinces, as well as coastal British Columbia. And this makes sense. Actually, these areas, these temperate forests, are where the growth rates are the highest typically in Canada. And they're areas that are close to roads, and there's a lot of area in these forest types that is in need of forest restoration. The other map that people ask me a lot about is the biodiversity one, and this is it here. So in essence, it showed a similar pattern the one that I just mentioned. And this is because, like growth rates, Canada has this, essentially like the world as a whole, there is what we call a latitudinal gradient in diversity, meaning that areas in the poles are species rich, and areas in the equator are species rich, and areas in the poles are relatively species poor. And you see this pattern playing out in Canada, which coincides nicely with the ecological productivity of these sites that just allows more life to occur and more diversity to occur. And so this map is a reflection of that pattern. So you'll see, as I mentioned, much of Canada's temperate forest in the south identified. And it also includes a lot of areas here in the Montane Cordillera ecozone of central British Columbia and western Alberta. And these areas were identified because they contain species that are really only found in those areas. So the model was just automatically drawn to those areas to find them and be representative of the type of diversity we see in species at risk in Canada. And I'll talk a little bit about the trade-offs and synergies that we found. And so we depicted these in two ways. The correlation matrix you see on the left shows the positive and negative relationships among our variables. So for instance, we found a strong and positive relationship between the occurrence of species at risk and high growth areas. This is, as I mentioned a minute ago, sort of the way that nature works. And so and then the main trade-off we identified was that high growth, high diversity areas are found where typically restoration costs and are the highest. And this is because these areas occur where there's a lot of competing land uses at play and where agricultural land values are the highest and where the deciduous trees tend to dominate and which are typically more expensive to regenerate than conifer trees. So in short, if we want to capitalize on the positive relationship that exists between species diversity and tree growth, we're going to have to pay more for it. The star plot on the right, you see, is a bit of a complicated figure, but essentially what it does is that for each of the scenarios we considered, it shows how they fared in terms of meeting all of the attributes that I described at the beginning of this talk. So each star in the star plot indicates how each scenario fared in terms of addressing the 7 variables of restoration interest. And so the best star plot in the case would be the one that's most widely distributed, and the worst one would be the one that's very narrow to the middle. And what you see here is that no one scenario actually did well at meeting all of the attributes, which again points to these trade-offs and synergies that are at play. And so last, we examined how the different scenarios fared regionally and how they do in terms of addressing the co-benefits that we examined in the study. And this figure attempts to illustrate that. And so what it is, it's 4 mini star plots like the one I just showed in the previous slide that essentially capture the kind of the co-benefits associated with forest restoration related to the people values and to the biodiversity values that we examined. And so what it indicates is that different regions do have different kind of spatial, let's call it configurations of how the co-benefits are distributed and how they're related to the growth rates of trees. And so for instance, mitigation focused scenarios, i.e. the ones that tried to capture the highest growth at low cost, did well in Eastern Canada at meeting all of the co-benefits that we care about or that we examine in this study. In British Columbia, in contrast, the best approach at maximizing the co-benefits is one that focuses on species at risk. And in Ontario and perhaps arguably in Alberta, a focus on freshwater provision may yield the highest co-benefits of all the variables that we examined. The take-home message here is that not one size fits all. Different factors come into play in different regional settings, and that really what's required in terms of designing a national level strategy for forest restoration is paying attention to those regional differences. And that, you know, the best thing to do in a particular site is a case-by-case situation. I'll now talk about 2 aspects of design, of national scale design for forest restoration that we didn't consider in an analytical way in our work, but that are really important for effective portfolio design. And so the first one that people really talk about is this idea of durability or permanence, meaning that if you're going to invest $100 in restoration, you want to make sure that that $100 lasts into time, and that it allows the trees the time they need to really hit their photosynthetic stride and provide all the benefits that trees can provide, which they don't do in short order. You know, trees take time. And really, some of the evidence that we've looked at is that we should be thinking about, at a minimum, as a 30-year window, and ideally much longer, to realize the benefits that people want from forest restoration. And so when we're thinking about national scale design of our portfolio, let's consider drought risk, and let's consider the risk of wildfire. And everything else being equal, we should focus attention on where drought risk is relatively low and where we don't anticipate an increasing risk of wildland fire, at least in the short term. And happily, I guess, is that these areas tend to coincide with Canada's temperate forest reign. And that's what you see here. Essentially, the climate models are indicating that, you know, the increase in fire risk that people see about and you see in the news, it's not a uniform pattern across Canada, and that the risk is variable in space across our nation. And that's what these maps reflect. The second thing to consider is this idea about albedo. And so, you know, the science of forest restoration and relying on nature to provide climate mitigation is evolving. And it's becoming increasingly clear that we need to pay attention to the albedo effect. And so the albedo effect, you probably know, is the land surface reflectivity of incoming solar radiation, i.e., what are the sun's rays doing when they hit the Earth? Dark land covers, like a coniferous forest, tend to absorb that radiation, and light land covers, like snowpacks, tend to reflect that. And so if you go from a light cover, like a snowy field, to a coniferous forest, you change that albedo. And so we need to pay attention to that as we're thinking about national scale design. And scientists have come up with a way of sort of creating an albedo deduction to account for that land cover change. And so we deduct this albedo effect on our estimates of how good any intervention is for helping us fight climate change. And so in this map by Hazard et al., the purple colors indicate locations where there's a high albedo deduction, and the green colors indicate where there's a relatively low albedo deduction. Again, fortunately, much of the area that we identified in our principal solution sets and scenarios occur where much of the offset is relatively low. And I will say, even in areas where there's a relatively high albedo offset, this impact can be mitigated through things like favoring lightly colored or relatively lighter colored deciduous trees over conifers. That introduces other complexities in terms of permanence and disease and site maintenance and other things like that. But it's worth favoring, in general, deciduous trees and forest restoration in a lot of the areas that we identify as priorities. So to sum up, there is lots of area in Canada to implement 2 billion trees and really forest restoration in general. And there's an opportunity to capitalize on the synergy that exists between the high growth of trees in our southern areas and temperate forests with the high density of species at risk and species that need interventions to help survive. There are lots of co-benefits available from forest restoration, just not all everywhere and all in the same places. So this indicates that we need a portfolio approach to optimize how 2 billion trees and forest restoration efforts can best meet all of the outcomes that people want. And lastly, I'll say that this considerable investment by Canada in forest restoration offers a chance to illustrate to the world and other significant restoration efforts on how forest restoration and in particular forest cover can best work as a natural climate solution and help provide all the things that people want from new forests. So that is the talk. I'm happy to take questions, and I see there's a couple in the chat. But Sharon, I'm not sure if how you want to handle the next steps.
Okay, thank you, Ronnie. That was a great presentation. Before moving on to the Q&A session, let's take a moment to fill out the post-webinar survey, and I'm gonna launch it now. So there are 2 questions in total. You may need to scroll down to see the next one. All right, Ronnie. So the first question for you is, given climate change and its potential impact on temperate regions identified by your models as promising under various scenarios, what are the chances that a large-scale effort to plant 2 billion trees will succeed with low mortality, considering the risks of increased drought and wildfires? Do these models also count for the climate adaptation potential of the replanted forests?
Well, a light question to begin with. So I will say that yeah, the chances are not uniformly distributed, and so the 2 things I mentioned at the end of the talk, one particular durability aspect, needs to be sort of firmly in mind as we think of project design and areas where we should be focusing forest restoration. You know, it's not possible to predict the future in a very certain way, but I think there are things that we can do to mitigate these risks, and in particular, I mentioned 2 of them. Let's focus on areas where we think that right now, currently, the drought risk is relatively low. So one thing that means is like, let's avoid tree planting projects in our prairies ecozone and other natural grasslands, which have a summertime drought as a natural part of the cycle. So let's not plant the trees there. And the other one is, let's focus on our areas where currently there is high annual precipitation, relatively speaking, and B, where that annual precipitation, particularly in the summer months, is expected to either be constant or actually in some cases increase into the future. So those are one way that we can think about mitigating that risk. In terms of accounting for the climate adaptation potential of planted forest, the short answer is no. We didn't consider that in this study, but it is obviously such an important consideration. And the reason we didn't consider it is that really it's a very site-specific issue, meaning the types of species choices you will make need to be mindful of the local needs of the communities, the types of climate pressures that a certain area is facing, and what the right species assemblage is that can best provide that adaptive capacity. In general, more is better. A diverse mix of species that includes, a focus on deciduous trees and, assuming we can overcome some of the regeneration challenges of that type of restoration, is better. The science is clear that mixed plantations tend to do better in the face of drought, and that they provide more carbon in the long term and more habitat for species at risk or just for life in general.
Thank you, Ronnie. Before moving on to the next question, I just want to quickly remind everyone that this session is being recorded and the recording link will soon be posted on the CIF Open Access eLecture webpage. Okay, moving on to the next question in the Q&A pod. For the purpose of the analysis, how did you define and measure landscape connectivity?
So for that, we relied on the study by Richard Pither. I should have actually, I'll do it before the end of the webinar, but I'll post a link to the study and you can get the data the source study yourself. Those data are also available online. And so landscape connectivity in this context, it's a bit complicated, but it was essentially assessed by what we call current density. And so these models of landscape connectivity essentially ask the question of where, it's like electricity moving through a circuit. And so rather than saying, modeling connectivity between one protected area and the next, they essentially assume all of the landscape is connected to some degree. And then they essentially, the model picks randomly any one spot and models connectivity to any one place around it. And it looks at the resistance surface, i.e., so a large water body would have a very high resistance, so that current would sort of flow around that large water body. Highways play the same role. And then the model, these studies kind of do this many, many times. And then they essentially provide a hot and cold map of how good any one area is to allowing flow through it. And that's the score that we used in this study.
Thank you, Ronnie. Next question for you is, in your opinion, what is the role of assisted migration in this type of reforestation effort?
I think it's an important consideration. I think assisted migration is part of that site level prescription that needs to be done in order to have a successful planting project. And in particular, I think we need to pay attention to a lot of things that, the practitioners are already being mindful of. What are the species that are drought adapted, but also still locally, that are local provenances, as I say. To the extent that we can build in these notions of assisted migration and do so in a way that's really mindful of the possible negative biodiversity consequences, we should actually be thinking about it. There's no doubt. It's hard to answer in a general way, but really, I think it's an important consideration, and people are already, I think, thinking about it. Really, the constraint that I've heard about in speaking to practitioners is about the availability of seed stock and tree planting stock, and to the extent that we can source those from areas that we expect are currently today what the climate in the future will be like, then we should definitely do that.
Thank you, Ronnie. Moving on to the next question is, can one focus on a specific area of interest and get these results to that area? Is there a website for this?
I'm very happy this question is asked. Yes, we all of the data from the study are publicly available. The study itself is open access, and it's consistent with the approach that we take to science here at Nature United, that we want no barriers to entry. We want to make all the data publicly accessible. And so when I post a link to the study that I'm talking about today, I'll also post a link to this mapper that we developed where you can examine the data yourself. I will caution against sort of pixel peeping, as they say. And so think about these data in the context of the broader analysis and the constraints and assumptions that went into those maps. And so just be mindful of those differences. But absolutely, I'll post a link and it's basically, it's natureunited.ca/reforestcan. But I'll put the link in the chat before we stop.
Thank you, Ronnie. So the next question in the Q&A pod is, thank you for the informative presentation. Have you tested the validity of your models by picking a specific province or region? In other words, ground truthing your series and assumptions.
What a great question. I will say that the evidence in this regard was something I was very pleased to hear. So I was at a conference in February by Forest Canada, which is one of the partners in this project. And they took the information that we created, which was done independently of their own efforts to bring forests back in Canada to do forest restoration. And they were able to take our area of opportunity analysis and our scenario results. And they said that the areas that we identified as priorities were already chosen by their staff as project areas, and that they had already planted over 15 million trees in these sites, which to me as a researcher who developed a national scale analysis was a very reassuring finding. So that wasn't part of the effort of this study, but it is, it does bode well for the fact that the data, the analysis that we presented are actually robust and that they have meaningful inferences possible from the ground.
Thank you, Ronnie. Next question for you is, how soon does newly exposed land areas become available for planting as glaciers retreat? What's your recommendation on how to consider these areas? Coastal BC.
I'd have to think about that more, but without the benefit of more reflection, I will say that they're probably not very good candidates for restoration, meaning that, I mean, relatively speaking, these areas, if the glaciers have just receded, it means that they're probably still, even though the weather and climate is changing, that are conducive to that retreat, that probably means that they're still experiencing less than ideal growing conditions in terms of, it's not southern Canada where the growth rates are high. So everything else being equal, I wouldn't choose those areas. Also, the evidence of kind of successful restocking of these areas is low. But I think it's worth considering them. I wouldn't do it as a first priority.
Thank you, Ronnie. Last question for you is, for the opportunity analysis, has there been any assessment of land ownership types, for example, Crown, TMOs, First Nation, with respect to the availability of financial support, such as government funding or carbon projects?
Yeah, good. I'm really appreciating these questions. So the short answer is no, we didn't do that in an explicit way, but we could actually. And so the original thinking for this project was that we were going to essentially conduct this analysis and then essentially do some rights holder and stakeholder mapping in the priority areas. So you could take the data that we created, identify areas, that look at good potential candidates for forest restoration. And then ask the questions like, who is the landowner, the land steward in these areas? And begin to devise an implementation program that's mindful of that ownership status. And so, for instance, in a lot of Southern Ontario, we expect them to be private land or municipal land. So those will be the partners to engage in that respect. It may be Indigenous lands. And so, in those cases, we would preferentially, we would look to those communities as partners. I will say, that the 2 billion trees program has a requirement that it needs to be additional. So they don't fund projects where forest restoration or regeneration in this case is already mandated by law. So after logging, for instance, in Canada, the provinces typically have a requirement on public land for the companies that did the logging to restock the areas. So those areas aren't qualifiable as potential projects for 2BT, and rightly so. If there's already an existing legal obligation, then this restoration wouldn't be additional, so we shouldn't consider it.
Thank you, Ronnie. If anyone has any follow-up questions for Ronnie after this webinar, please feel free to reach out to us and we will help connect you with him. All right, if there are no more questions, I would like to bring this session to a close. Thank you all for participating in our CIF electronic lectures. And thank you once again very much to Ronnie for this great presentation. Bye, everyone.
Thanks a lot.